All right, everybody. Here we have Unit 9 and 10 Mom review. This is going to be largely T intervals and T tests, but there is a little bit on the bottom about proportions, I believe. So let's get into it. Number one is reminding you how to find a critical value. And since we're doing a sample mean, it's a t value. So you take your sample size minus 1, and then you look at table B. I've already highlighted it. Table B, right here, table B, 27 degrees of freedom, 95%, so there's your answer, 2.052. And I'm not even sure how it wants to round, so just be careful of that. Number two, here's the confidence interval. You'll have your own numbers, of course. And we're looking for the point estimate, which is just the center. Okay. In this case, it would be an X bar because these are not proportions, these look like means. Once you draw this, it's pretty darn obvious. You just got to find the center, add up and divide by 2, negative 9.6. 0.6 plus 225.4 divided by 2. That's your middle. So 107 for me. And then as well, the margin of error is next. The margin of error is simply how far we go up and down from the middle. So I can just take my maximum value and subtract the center. I could also take the center and subtract the minimum of negative 9.6. And either way, I see what I have is that the margin of error, it's 107.9 in the middle, plus or minus 117.5 for the margin of error. Number 3 gives us sample size, sample mean, standard deviation S, and we are looking for the margin of error. Okay. So well, you could, if you want to use the calculator heavily, you could just take all this and you could put it in the calculator. Tests, it is a t-test, one sample t-test, number 2. And, not a test, I'm sorry, an interval, because intervals create margins of error. So I'm looking for number 8, t interval. Put in what they gave you, 39, S is 6, and sample size is 11. Confidence percentage is 98. And you can see there, they're giving me the interval. And I'm going to just sketch it. It goes from 34.0. Oh, that's nice, to like 44, if you round that. So that's pretty nice. It looks like the middle is 39, which makes the margin of error pretty darn easy. It's plus 5 and minus 5. Now, another way to go about this is to just know that this formula is the margin of error of a t interval. I'm going to go back to my formula sheet, go back to it. Your general formula for an interval is right here. It is your statistic, in this case, x bar, plus or minus your critical value, in this case, it's a t star, and then your standard error of the statistic. You might be wondering, what is that? You go down here, because we're doing means, right, for a single sample, because we have an x bar, and here's the standard error, right there. S divided by square root of n. And they gave us that, right? They gave us S. So it really wouldn't be that hard to just calculate this. We do need to remember, for me, I believe my n was 11. So my degrees of freedom is 11 minus 1. What was my confidence percentage? 98. So I'm going to go down to table B again, combine with my degrees of freedom, and find my T, my critical value. So I'm at 10, and I'm at 98. So 98, so 2764. Let me see if I can remember that. So piecing this together, I know my T is 2.764. Okay. My S sub x is 6, and my square root number will be 11. Let's just see, this should work out to be about 5, because that's what I got right here by creating the interval first. So 2.764 times 6 divided by the square root of 11. 5,000. Well, that's because I missed my decimal. There we go. So either way you slice it, margin of error, 5. Okay. Moving on. Number 4, it says here's a 95% confidence interval for the weight of a small package of M&Ms. It's between 47.82 and 48.16. In other words, what we're asking here is, what does that interpretation mean? This is when we have used that sentence frame. We are 95% confident of what? And we are 95% confident that the true weight, the true weight of a small package of M&Ms is in here, which is what the last one is saying. The other ones are all incorrect interpretations. We're not saying 95% of all packages weigh that. No. When we took a sample, we created this interval by, we made our curve. We had our X bar in the middle, and then we went from the middle, we went this way and this way, the margin of error, to capture 95%. So we're saying that we believe when this interval that we've created, we're 95% confident that the truth is in there, that the true mean weight of packages will be in this interval. Number 5, it gives you information, it gives you sample size. People were asked how much they spent on their kid's last birthday gift. The results were bell-shaped, that's nice. Here's X bar, that's $49. Standard deviation, that's S of X, and make a 90% interval. So this is a one sample T interval. I'm just going to use the T at 84. It's button number 8, and just put in the information. Pretty easy. Once you identify it, sample size was 18 people. Confidence percentage is 90 for me. And there you go, and just put your interval there. So mine goes from 45.3 to 52.7. Spent anywhere from $45 to $52. We're 90% confident that the average amount of money spent on a kid's birthday gift is between those $2 amounts. Number 6. Now we're doing a test, not an interval. It gives us the null is the average is 30.8. The alternative is a one-sided test that it is less than 30.8. We got N, X bar, and S. It simply says, what's the test statistic? If you were a glutton for punishment, you could be like, oh, okay, we take X bar minus mu. Here's the formula if you wanted to go the long way. So you do 30 minus 30.8 divided by 2.08 over the square root of 45. And while I'm at it, I might as well show you. This is on the College Board packet, folks. just like that interval was, so are test statistics right here above it. It says any test statistic is the statistic, in this case that's x bar, minus the parameter, in this case it's mu, and then the standard error of the statistic. Remember what it was earlier, it's the same thing. It's a single population x bar, single population mean. And here's the standard error one more time. So the standard error, this denominator is s of x divided by root n, which is what I just did right here. So let's see. This is the long way, but let's just try it anyway. So 30 minus 30.8 equals, divided by parenthesis 2.08 divided by root 45. So I'm getting the test statistic of that, negative 2.58. Let's just verify on the calculator. When I run a t-test, this is a test, and put in the information, mu 0 is the null, x bar was 30, s sub x is 2.08, sample size was 45. I need to pick the less than. Yep, and there it is, negative 2.58, and it gives me the p-value as well. Just take your answer here and put it in the right spot to 2 decimals. All right, number 7. We are testing the following claim. Here's your null and alternative. Alpha is 0.05. We believe they're normally distributed. Okay, so we can move forward with this. The sample sizes are, well, here's the information about sample 1. Here's the information about sample number 2. What's the test statistic? So this is 2 sample, right? Because we have N1 and we have N2. So that is button. That is test number 4. See it there? 2 sample t-test. And then be very careful just entering your numbers. My first standard deviation is 6.9. My first sample size is 17. My second sample on the next row, I'm looking here now for these numbers. 14.1, 21 is the sample size. And then what is the alternative? It is a greater than, and I'm not going to pool. It was selected. Remember, don't pool, which will change your decimal a little bit, which will matter for the mom. So I'm getting the test statistic of 2.51. It says what's the p-value? It's right underneath it, minus 0.008. Accurate to 2 decimals. So I would be rounding mine to 0.01. The p-value is less than alpha because 0.01 is less than 0.05. This leads us to reject the null. And what's our final conclusion? Because our p-value is less than alpha, well, it's not greater than alpha, it's not greater than alpha, so get rid of those two. It would be we reject the null, so it's this one. And then it's probably worth your time just to read the final sentence. So there is significant evidence to support the claim that the population mean is greater than the second population mean, that the first mean is greater than the second mean. All right, number 8. I've highlighted the 2 samples. The orange one is people who lived in a city that identified as a gambler, and the green one is people in a rural area who identified as a gambler. We're going to make a interval for the difference in proportion. So key here is when I see this right here, difference in proportion, I know it's a 2 sample because it's the difference between 2, and proportion helps me know that it's a proportion, it's a p. So we're doing a 2 sample interval for like p1 minus p2. P1 would be the proportion of people in the city that gamble, right? This would be the city folk, and this would be the country folk, rural, okay? That's just the idea. I can pretty much have my calculator do all the work for me, but identifying it is of supreme importance, right? It's not an X bar, it's not an average. We have, for example, P1 is 72 people out of 263 people. P2 is the people in the country, 61 out of 116. So off the get-go, let's just see how these compare. We have 27% in the city that reported being gamblers, and in the country, whoa, it's like double almost. So, I'm just trying to look here before I go. I think I'm going to do city minus rural. Um, so in other words, I'm going to do 0.27 minus 0.53. Um, that I'm kind of doing as much as I can without using the calculator button. So my interval is going to be centered at negative 0.26, the middle of it, and then it'll have endpoints, obviously. We'll get the margin of error from the calculator, and it will find how far we go either way. So let's go to stat tests. This is a two-sample t interval, number 0, and sorry, it's not a two-sample t interval. That's a mistake. It's a two-sample proportion interval. When I said t, that was wrong. It's a two-sample prop interval because it's a proportion. It's not a mean. That would be number 9. Nope. Where am I looking? That's B. Thank you, Feig. B, 2 prop Z interval. There we go. And this menu fits what we are given anyway, right? X1, that'll be the orange. That'll be the people in the city. 72 people gambled out of 263. X2 is 61 people gambled of 116. Confidence level 98. So there you have it. They're giving me the interval. The low end is negative 0.377. The high side is negative 0.126. And if you round to 2 decimals, you can put that up there. Real quick, I'm just curious. This is what I do. If you add this up and divide by 2, you should get that if I did my work right. So negative 0.377 plus negative 0.126 divided by 2. No, it's not perfect. It's not perfect. I wonder if there's some rounding. Maybe this has been rounded a little, which is affecting this a little bit. It's not so far off that I feel terrible about it. Okay, there's your interval. Number 9. Here's another proportion. Proportion of men who own cats is different than the proportion of women who own cats. So proportions, 2 proportion test. Is it significantly different? Right here is why we're going to choose the not equal to option for me. If yours says greater than or less than, you would be here on this one or this one. Notice I have crossed these off because they're mu's. They are set up to be means, but we don't have means, okay? If you had a not equal to, that's two-sided, okay? If you had a greater than, that would be the right tail. If you had a less than, that would be a left tail. All right, here is the sample, okay? And we need to do a two-sample proportion z-test because they want the test statistic, the p-value, and then our final conclusion. Now, when you go to this menu, two-sample proportion z-test, That's number 6. Notice it wants x1 and n1. Well, I don't actually have x1 right now. I have the percentage. So for me, x1 will be my sample size times, it'll be n times p. So sample size of 20 times 0.3, 0.30, which is 6, right? 30% of 20. 30, not, there we go. And then my x2 would be that n times, well, I guess this would be n1 p1, this will be n2 p2. I'd have 80 times 45%. I have to have the number of successes. If I was actually doing my conditions, this would be a bit of a problem. I don't have 10 successes for the men. I guess men hate cats. But it's not asking me about that. So we're just going to press on button number 6. Now I have what I need. 6 men had a cat out of 20. The women, the females, 36 over 80. And there's my test statistic, negative 1.22. If you round it, my p-value, oh, wait a minute. Oop, I got to pick the right alternative, right? Is a not equal to. It does not change my z, my test statistic, but it does change my p. So I'm getting 22. Based on that, we will not reject the null because 0.22 is above really any alpha we've ever had. Did it give me an alpha up here? Yep, it gave me an alpha of 0.05. So I'm not going to reject the null. Number 10, last one. Oh, yeah, last one. We want to know if a new feed increases the mean weight gain compared to an old feed. Maybe this is a farmer raising cattle or something. At the conclusion of the experiment, it was found the new feed gave a 10 kilogram bigger gain than the old feed. A 2-sample t-test with the proper one-sided alternative was done, and the resulting p-value was 0.082. This means that blank. Okay, so this is just having you interpret the p-value, okay? What does this 8% mean? And I tried to draw a picture to help you, right? This is the difference in the weight. They had the old feed, it looks like oid. They had the old feed and the new feed, right? And they had a sample, presumably with the cows getting the old feed, and then another sample with the cows getting the new feed, and then they are subtracting them. And it says here that they found the new feed gave 10 kilograms bigger, 10 kilogram gain. So that would be here. This is essentially the sample result. This is x1 minus x2, if you want to think of it that way. It's the new minus the old. The null would be that mu new equals mu old, right? And that's here, that there would be no difference. And the alternative is that the mu new helps them gain weight, so it would be bigger than mu old. This is all just set up to help you understand, right? So the whole setup is based on the null being true. So if there is no difference between the new and the old feed, then this result of 10 or more will happen 8% of the time by chance. So I can, it's not this one. See, it says assuming the null is false. We assume the null is true, okay? That's how you always start interpretations of the p-value, okay? This is not it's not the percent chance it's true, okay? It's not that. You're not assuming the null is false. You're assuming the null is true, ding, ding, ding. It's B. Assuming the null is true, there is an 8% chance of this difference or greater of getting a sample with a difference of 10 kilograms or more. So it is B. D is a distraction too. There's an 8% chance the alternative is true. This is not, it's just this testing, if you understand the setup of the entire test, okay? Um, and this is not right because it says there's an 8% chance of getting exactly a 10 kilogram increase. It's more of a CDF rather than a precise outcome, folks. It's 10 or greater. So that's close. There's an 8% chance of getting a 10 kilogram increase or greater, assuming the null is true. So there you go. Enjoy.